All right. So this afternoon we are going to start with something called rotational work, energy, rotational energy, and also rotational momentum. Now, from just the title, you can see that this, when you talk about rotational work, when you talk about rotational energy and rotational energy and momentum, these physical quantities, work, energy, and momentum, look like and sound like stuff which we have already looked at. Yes, we have done that. We have looked at what work is, we have looked at what energy is, we have also looked at linear momentum. But that time when we were looking at them, we were looking at these things when the object we were looking at, or the objects we were studying, were moving in a straight line. So when we looked at work, we looked at energy, we're looking at it in terms of an object which was moving in a straight line. The same thing applies with momentum. We looked at something called linear momentum and impulse. The linear in momentum means that the object was moving in a straight line. Now, as you can see from the titles, there is a suggestion that actually work has got a rotational counterpart or a circular counterpart, which is what we're calling rotational work. And there's also energy which exists when an object is moving in a circle, and there's also linear momentum which exists when an object is moving in a circle, and that's what we are going to look at. This should not be very surprising because so far we have looked at certain physical quantities which actually have rotational counterparts. For example, we looked at linear displacement S, and linear displacement S has got the rotational counterpart which is angular displacement. We looked at velocity, or linear velocity, and linear velocity had a rotational counterpart which is angular velocity. We looked at linear acceleration or tangential acceleration, and that one also had something which was called angular acceleration. We went further. We looked at some equations of motion. We had V is equals to U plus AT. For that one, we had omega F is equals to omega I plus alpha T. Then we also had the rest of the other equations of motions. So it should not surprise anyone that this relationship, these physical quantities, work, force, momentum, energy, power, they have got their own rotational counterparts, and that's exactly what we are going to look at and what they are. The first one we're going to look at is what is called torque, or the moment of a force. Now, we have seen when we were looking at Newton's second law of motion, F is equals to M plus A. F is equals to MA. From Newton's second law of motion, we learned that when you have a mass of mass M, and this mass undergoes an acceleration, there has to be a force which is causing that particular acceleration. So from Newton's second law of motion, what we learned was that if you have got a force, that force can cause an object to accelerate. However, that is not the only thing which force can do. Force can also cause an object to turn or to rotate. Is it clear? A force can cause an object to turn or to rotate. Now, when you have a force, then you use this force to rotate an object or to cause an object to turn, so that this particular object, you use the force to cause an object to undergo rotational motion. The amount of rotational motion you are going to give this particular object as a result of the force which you are applying on this object, that is what is called torque. The amount of rotational motion or the amount of turning effects which a force is going to cause, that is what is called torque, or sometimes it's also called moment of a force. when you have a force, sometimes the same force can cause a lot of torque, turning effect. Other times, it might not cause turning effects. It depends on what's happening. Okay? So, the same way, when you have when you're talking about linear motion, force causes an object's velocity to change. So in that case, when you're in a straight line, we say that force causes a change in linear motion. So if there's a force, then the velocity of the object is going to change. So force in a straight line, when an object is moving in a straight line, force is what causes a change in the motion of the object. The motion of an object is measured in terms of linear momentum. So when the velocity of an object changes, its linear momentum changes. If the linear momentum changes, then we say that the motion has changed. So when you're in a straight line, when an object is moving in a straight line, force is what causes an object to change. Okay? However, when an object is moving in a circle, the thing which force does, that is what torque does. The torque is the force. The torque produces the same kind of effect as the force when an object is moving. So if there is a torque, then an object is going to rotate faster. Whether it's moving in a circle or it is rotating about a fixed axle like a tire. So a tire is connected to an axle. So if there is a torque, then an object is going to rotate faster. So when you're in a straight line, when you're talking about straight line things, you talk about force. Force causes an object to move faster and faster in a straight line. However, when you are talking about rotational motion, then you do not talk about force, but you talk about torque or moment of a force. Moment of a force is what causes an object moving in a undergoing circular motion to move faster and faster. Are we clear?
Sir.
Yes.
I have a question, sir.
Go ahead.
So that force, it can also be called tangential force or what?
Which force?
The same force which is applied to the rotating object.
Sometimes if you apply it at the tangent, yes. But other times you don't have to apply it at the tangent. It's just a force. So this force has got a point where it's being applied on this particular object. So you can apply it so that it comes out as a tangential force, that's okay. But other times you can apply it, then it doesn't come out as a tangential force. It's just a force.
Okay, thank you, sir.
Yes. Now, for a force itself is not enough to cause torque. Torque depends on force. Yes, you need a force to be there, but the mere fact that you have got a force does not necessarily produce a torque. Is it clear? Having a force is not enough, is not sufficient for you to produce a torque. There has to be this other bit here, this R theta. There has to be this other bit here, this R theta here. For you to produce torque, you need to have a force, then you multiply this force times this R, then theta. The theta bit, the R, is telling you that if the force, between the force where the force is acting and the axis of rotation. So if you look at this diagram here, this at the center here is the axis of rotation. So between the axis of rotation and the point where you are applying the force, there has to be some distance. There has to be a separation between a force, the direction of the force, and the axis of rotation. This red line here. So if you get this line, this force here, which I'm applying here, which is the applied force, if I shift this applied force, then I make this force pass through the axis of rotation. there will be no error. The error is going to become 0. So the first thing which is required is that there has to be a radius, or there has to be some distance from the axis of rotation to where you are applying the force. Is it clear? There has to be a distance, some separation distance between the axis of rotation and the point of application of the force. This distance is what you refer to as error. Is it clear?
Yes, sir.
So that's what the error is doing. The error is the distance from the axis of rotation to the point of application of the force. So as you can see from here, the larger the force, the more torque you expect to produce. But there has to be a separation distance between the axis of rotation of the force and the point of application. The other thing which is needed is what you're seeing, the third part here, which is sine theta. Now, if you look at this here, the theta is this one here. That's what we've been given as theta here. But this theta here is also equals to the angle here between this red line, which is the error, and this force, which is a force, applied force. The angle between error and the applied force. This angle between error and the applied force is also theta, because you are using what are known as corresponding, is it corresponding or alternating angles? I'm not sure exactly. Alternating angles, I think. Yes, alternating angles. Are we clear? So this theta which you have here, is the same angle which you have here. There. Are we clear?
No, sir. Now, I've got a question.
The theta, are you seeing this theta which you have here? Are you seeing this theta here?
Yes, we are seeing it.
This theta, if you use alternating... First, let me speak. This theta, if you use alternating angles, this angle between this dotted line and the red line, this angle is the same as this angle between this red line and this black line. Here. Is it clear?
Yes, sir.
So this angle theta is very important. And that's where the other person was asking, say, do you have to apply the force tangentially or not? Well, if you are going to apply a force tangentially, it means that the angle between this red line and this black line, which is representing the applied force, the angle is going to be 90 degrees. If the angle is going to be 90 degrees, then sine 90 degrees, if you've got a calculator nearby, you're going to find out that sine 90 degrees is equals to 1. So sine has got a maximum value of 1. So what is this telling us? Apart from having an applied force, and also apart from having a separation distance between the axis of rotation and the point of application of the force, you also need to have this sine theta. And this sine theta, depending on what the angle is, if the angle is 90 degrees, sine theta is going to be 1, and you are going to have maximum torque, or you're going to produce maximum turning effects. Is that clear? Error is a distance from the axis of rotation to the point where the force is being applied. From the axis of rotation to the point where the force is being applied, that is your error. The angle between error and the direction in which the force is being applied, that is your theta here. So torque also depends on what theta is, so that you end up having sine theta. Now, if there is no angle, let's say the angle is 0 or whatever it is. If theta is equal to 0, then you don't have a torque. If theta is equal to 180 degrees, you don't have a torque. So there are times when you apply a force, but the way you are applying a force, from the point of application, if you apply a force and between R and how you have applied force, the angle is maybe 0 or 180 degrees, you will not be able to produce any torque. Are we clear?
Sure, sir.
Yeah. There was a question. What was the question? Someone had a question? Okay. So, the turning effect of a force depends on the size of the applied force. It depends on this separation distance between the axis of rotation and the point of application of the force, which is R, and it also depends on this sine theta, like that. Now, if you do something, if you from here, like that, this R, which we have here, our angle here is theta. Our angle here is theta. Then we also have got theta here. Then you end this line here. From this line here, R sine theta. This R sine theta is also what's referred to as a lever arm. R sine theta is also what's referred to as a lever arm. So your torque depends on the applied force. It depends on the rate, on the distance from the axis of rotation to the point of application of the force. It also depends on theta. Theta is just the angle between R and the direction in which the force is pointing. So that should give you your turning effects, or it should give you your torque. Any questions?
Sir,
Yes.
so you are saying that in order for us to have the torque, you mean that the product of the force should be perpendicular between the distance and the application of force of the pivot.
When it's perpendicular, then the torque is maximum. You can have torque, okay, you can have no torque. That's not the point. The point is, if you want to have maximum torque, then the angle theta must be 90 degrees. You only have maximum torque when the angle theta is 90 degrees. But the rest of the time, you can also have torque. But the torque is not going to be maximum.
Okay, clear, sir.
Okay. So if your angle is 20 degrees, you still have torque, but your torque is not going to be maximum. Okay.
Now, sir.
Yes.
Which one would be the angle if maybe, for instance, you're rotating a ball horizontally?
Your what?
You are rotating, or I don't know if it's called whirling. You are rotating something around. Now you want to calculate the torque in a horizontal way.
You want to calculate the torque in a horizontal way.
Yes. Now which one are you going to take as your angle?
Usually, when it comes to torque, usually our focus is the situation you have presented is what can I say? Not very clear. But when it comes to torque, we look at things like tires, things which are rotating on an axle. So in such a case, when something is going round, the axis of rotation is at the center, then the force is what? The force is passing through the center, because remember, if the example you're presenting, basically that's an example which has to do with centripetal motion, if I'm not mistaken. Is it?
Yes, sir.
Yeah, so if it's something which has to do with centripetal motion, it means that the force is always pointing at the center, right?
Yes, sir.
But the problem is, if a force is going to point at the center, then this R, remember, there has to be a distance, a separation between the axis of rotation and the direction in which the force is pointing.
Yes.
So if this force, which we have here, this black line, since you've got an object this side, you want this object to move around in a circle like that, then this force, if this force is going to point towards the center here, then there will be no R. R is going to be 0. So in such a case, you cannot produce a torque. Your object, which is moving in a circle, is not going to be turning. As much as it's moving in a circle, it's not going to experience a turning effect. Actually, there's no turning effect. Do you ever see a turning effect when you're whirling something in a circle? The object at the end of the rope, does it turn? Does it spin?
No, sir.
It never spins. The reason why it never spins is because the force, the centripetal force, passes through this axis. If we take the center as the axis, it passes through this axis, and the R is going to be 0. The separation distance between the axis of rotation and the direction in which the force is being applied, that R is going to be 0. If R is going to be 0, then there's going to be no torque here. FR sin theta, there's going to be no torque. So in such cases, we don't really look at torque in such cases. We look at torque in cases where an object is rotating on an axis, like a tire of a car or a ball which is spinning. Like planets spin on their axis. When planets are spinning on their axis, or when someone kicks a ball, then it starts spinning on its own axis. Those are the cases we look at when it comes to torque. Any other question? Okay, so if you don't have a question, this is example number 1. A force of 200 newtons acts tangentially on the rim of a wheel 25 centimeters in radius. Find the torque. So this is the kind of stuff we have. Objects which are rotating on an axis, like a wheel. So the torque is 200. We are told that it's acting tangentially, meaning that the angle between the distance, the angle between the radius of the wheel, which is the distance from the axis of rotation to the point of application where your force is being applied, that angle is 90 degrees, and the R, of course, we've been told the R is 25 centimeters. So in that case, you can work out the torque. Your torque is going to be the force you're applying multiplied by the radius multiplied by sin 90. So in this case, you're going to have 200 newtons multiplied by 0.25 meters multiplied by sin 90, and you're going to end up having a torque of 50 Newton meter. Are we clear? Are we clear? Yes. There is a reason why, if any of you has pushed a tire, maybe you're pushing a tire to somewhere, or you have played with the tire. There is a reason why you used to push the tire the way you used to push it. You push the tire from the top. Then you apply a force tangentially to the tangent of the surface of the tire. The reason why you used to do that is because that's how you produce maximum torque. You push the tire from the top. So when you push the tire from the top, where you are touching the tire, that is the point of application of the force. So the distance from the center of the tire to there, that is your R. So your R makes an angle of 90 degrees with your arm. That's how people push tires like that. That's the reason why you push a tire from the top, so that you can produce maximum torque. Is it clear?
Yes, sir.
Okay. So, basically,
excuse me.
yes, your question?
No, there's quite a number of people that are trying to join the lecture, but they are failing. What
Oh,
is
we
the
have not
problem?
admitted them.
Yeah.
They've been admitted now. Okay. The next thing we're going to look at is something called moment of inertia. Now, we have seen that when you talk about force, force causes an object's velocity to change. And force, we talk about force when things are moving in a straight line. When an object is moving in a circle or it's spinning on its axis, we do not talk about torque. So we do not talk about force, but we talk about torque. Okay. Now something similar also happens to mass. When an object is moving in a straight line, then the measure of how much resistance this particular object offers, when you try to apply a force, then this particular object is refusing to move or it's refusing to stop. That is what's called mass. Mass is a measure of inertia. Are we clear? Mass is a measure of inertia. If you try to push an object, the more it refuses to move, the more mass that particular object has. If you're trying to stop an object, the more it refuses to stop, the more mass that particular object has. So mass is a measure of inertia, but you only talk about mass when an object is moving in a straight line. Now, when an object is rotating or when an object is spinning, you also experience the same thing. When you try to turn this object, it's not going to turn right away. It will offer resistance. When you apply a force, then you try to turn something, it's going to offer resistance. So basically, there is something called rotational inertia or rotational mass. The mass of a rotating object. The mass of a rotating object, that is what is called the moment of inertia. Are we clear? Mass of an object is when an object is moving in a straight line. When the same object is moving in a circle or when the same object is rotating, we do not talk about mass. We talk about moment of inertia. Is it clear? Mass is in a straight line. So you've got an object moving in a straight line. The inertia of that particular object moving in a straight line, that is what's called mass. When you've got an object spinning moving in a circle, or when you've got an object spinning on its axis, the inertia of this particular object which is rotating, that's what's called moment of inertia. Okay. So moment of inertia is basically mass when an object is spinning. Moment of inertia is the rotational counterpart of mass in a straight line. If an object that is free to rotate about an axis is difficult to set in motion, that's the same explanation we've been talking about. So if an object that is free to rotate about an axis, for example, like a tire, so if you've got a tire, then you want to rotate the tire, then you've got difficulty rotating it, its moment of inertia about that particular axis is large. On the other hand, if you've got an object which has got a small moment of inertia, then you try to rotate this particular object, it will easily rotate. So how do you work out the moment of inertia? Well, it depends on what kind of masses you have. If you have masses you can count, and these masses you can count are connected to an axis of rotation, okay, so if you have masses, what you call, if you have got discrete masses which are connected to an axis of rotation. So consider an object that is free to rotate about an axis that is made up of tiny masses. So if you have got an object, then this particular thing is made up of different masses, and these masses are rotating about the same axis. So you've got mass 1, you've got a mass 2, and you've got a mass 3, and these masses M1 and M2 and M3 are separated from the axis of rotation by distances R1, R2, and R3 from the axis of rotation. So they are rotating from the same axis, but these masses are located at different distances. Then you can work out the moment of inertia, which is the resistance which the particular object is going to offer to your torque I, as follows. I is going to be M1 multiplied by R1 squared plus M2 multiplied by R2 squared plus M3 multiplied by R3 squared. So this is how you work out the moment of inertia if you have an object, if you've got a bunch of different objects rotating about the same axis of rotation and they are different distances. So basically what you're doing here is, what you have up here is, this is basically a summation. So you end up having this. The moment of inertia I is going to be equal to basically a summation of Mi. So whether it's a ith object multiplied by Ri squared. I don't know if do I have an image. No, I don't have an image of that. Okay. However, so this is one way. If you have masses, you can count, which are rotating about the same axis of rotation. You can do that like this, where Mi is the mass of the ith object and R is the distance from the ith object to the axis of rotation. So moment of inertia, as you can see, you have mass, which is measured in kgs. You have got the radius, which is just a distance, which is measured in meters. Okay, so moment of inertia has got units of kgs meter squared. However, there is also another way of working out moment of inertia, which is much less cumbersome. So there is this way, but there's another way of working out moment of inertia, which is this one, which you have here, equation number 4. I is equal to m multiplied by k squared. So in this case, m is the mass of an object, then k is something called radius of gyration. Now we use this expression I is equal to mk squared for some mass which is spinning on an axis. For example, a tire or a planet or anything which is just spinning on its own axis. Okay. So m is the mass of the particular object in kgs. K is the radius of gyration. Now k, which is the radius of gyration, is basically the average distance of all the particles which make up this particular object from the axis of rotation. This particular object, whatever object you're looking at, that object is made up of atoms. And if there is a particular axis of rotation, those atoms and the atoms which make up this particular object are located at different distances from the axis of rotation. So since usually these particular objects are made of billions of atoms, we do not consider the individual distances of these particular objects, but instead what we end up using is an average distance of all these particular particles which make up this object from the axis of rotation, and that average distance of all the particles which make up this particular object from the axis of rotation, that is what is called the radius of gyration. Are we clear on what radius of gyration is? It is the average distance of all the particles making up an object from the axis of rotation. So instead of using individual radiuses, individual distances of an atom from the axis of rotation, we end up using an average. Now this average distance from the axis of rotation depends on the shape of the object which is rotating. Different shapes of objects have got different radiuses of gyration. This is something which you're supposed to keep in mind. Different shapes have got different radiuses of gyration. So depending on the shape which you have, and depending on how that particular object is rotating, you will end up having a different radius of gyration. As you can see in this particular table here, you can have an object like a hollow cylinder, like this, a hollow cylinder, or a hoop, a hollow cylinder or a hoop. That's the same shape which a tire has. Or you can have a disc like this, rotating on its axis. So you can have a hollow cylinder like that rotating on its axis, or you can have a disc like this rotating on an axis, or you can have a rod like this one rotating about an axis, or you can have a rectangular block which is rotating about an axis, or you can have a sphere which is rotating about an axis like this. These are different objects. They were different shapes. So depending on the shape, you end up with a different moment of inertia. So remember, moment of inertia is m k squared. That's what moment of inertia is. Moment of inertia is m k squared. So in our case here, if you look at this table, for all these shapes which you have up here, the hollow cylinder, the uniform disc, uniform rod, uniform rectangular block, and the uniform sphere, they are already expressions which scientists have come up with, which scientists and engineers have come up with to express what the moment of inertia is supposed to be. If you have got a hoop or a hollow cylinder, the moment of inertia I is going to be equal to the mass of that particular cylinder or hoop multiplied by the radius. So if you've got something like this here, like this, the moment of inertia of this thing is going to be equal to the mass of this particular thing multiplied by that radius squared. That will be the moment of inertia. If you have got a cylindrical, a uniform disc or a cylinder also, so for a uniform disc or a cylinder, the moment of inertia is going to be half m squared. So in this case here, where you've got moment of inertia, m is equals to, I is equals to m k squared. This, sorry, r squared. This r squared is equals to your k squared. So in this case, your k, I think I need to update these notes so that I can add a table for what the moment of inertia is. Sorry, your radius of gyration is your k. So your k in this case is just going to be r. But in this case where what moment of inertia equals to half m, then r squared, in this case your k squared is equals to half r squared. So in that case you end up having the square root of, you end up having your k as r divided by the square root of 2. Similarly, for a uniform rod, your moment of inertia is equals to half m l squared. So this is how you work out your moment of inertia for a rod. For a rectangular block, your moment of inertia I is equals to half a squared plus b squared. So in this case, you're looking at this size. What is the side this side in meters? What is that side in meters? So you work out your moment of inertia like that. For a sphere, like this, your moment of inertia is going to be equal to 2 over 5 mr squared. Now, the thing is, when it comes to these moment of inertia things, if you want to find out what they are supposed to be, there's some complex calculations which have to be done. And in this course, you are not required to know how to find out, how to come up with these expressions. Those things are reserved for some advanced physics courses, maybe, I think in second year. If you are studying physics, those who study physics in second year, we expect them to know how to come up with these expressions. But for you who are trying to become medical doctors, we do not expect you to know how to come up with these equations, these expressions, but we expect you to know what these expressions mean and how to use them and what they stand for. Are we clear?
Yes, sir.
Okay, so let's have a look at an example. Okay, so a wheel of mass 6 kg and radius of gyration. So in this case, a wheel of mass of the wheel is 6 kg and the radius of gyration 40 centimeters is rotating at 300 revolutions per minute. Find its moment of inertia. Now, for you to, if you know what the mass of the object is, you also know what the radius of gyration is, which is the average distance of all the particles which make up this particular object. With that information, you can straight away find what the moment of inertia is. The moment of inertia I is going to be the mass of that particular object multiplied by the radius of gyration squared. You can find the moment of inertia straight away without having to bother about how fast this particular thing is rotating, because it's not necessary for you to know. Are we clear? So the moment of inertia, for you to find the moment of inertia, the mass of the particular object is 6 kg, and we know that the moment of inertia I is equal to the mass of the object times the radius of gyration. We have been told the radius of gyration is 40 centimeters. So I is equal to mk squared. So in this case, if you got a wheel, for a wheel, we know our moment of inertia I is equal to mr. So if moment of inertia I is equal to mk squared and moment of inertia for a wheel I is equal to mr squared, then you can see that if you compare this mk squared and you compare this for a wheel mr squared, for a wheel, a moment of inertia, a wheel is a hollow, it's like a hoop or a hollow cylinder. Anything with that shape, moment of inertia is given by this expression mr squared. So in that case, you will see that your radius of gyration k squared is equal to r squared, and you end up with this. Your radius of gyration is actually equal to the radius, which is equal to 0.4 meters, and you can work out what your moment of inertia is going to be. So I is going to be equal to the mass times the radius of gyration. So your I moment of inertia is going to be 6 kg times 0.4 squared, and you end up having your moment of inertia as 0.96 kgs meter squared. So this is your moment of inertia. So finding out the moment of inertia, if you know the mass and you know the radius of gyration, is straightforward. Are we clear?
Yes, sir.
Okay.
Sir,
Yes.
I have a question.
Mm-hmm.
Yes, sir. On the units, on the SI units there. So if they give us that the mass given is in grams, do we necessarily have to change it to kilograms? Or
Yes, you have to change it to kilograms.
Oh, okay. All right,
If your mass is in grams, you change it to kilograms. If your radius is in centimeters, you have to change it to meters.
All right, thank you, sir.
Okay. Next question is, what's coming after this class?
Chemistry.
Okay. What time is chemistry? 15? What time is your chemistry?
4 p.m.
At 4 p.m. So can
Yes, sir.
we because I don't know if because we have a lot of things to cover. I don't know if you're going to manage. At least if you can reach 10 pages, if we can reach page 10 of these notes, then I know that by the time when we look at Thursday, we can do a lot of things. So I don't know. So I'll probably ask you guys for another 30 minutes before we after 15 hours. So ask for 30 minutes or 20 minutes so that we can reach somewhere page 10 or something like that. Okay. I don't know how that is, but I'm trying to help for the quiz because your quiz is on Friday and all this material has to be covered. Okay, so the next thing is Newton's second law of motion. Now, what we know as Newton's second law of motion is in terms of F. F is equals to mass times acceleration, where F is the resultant force, M is the mass, and A is acceleration. Now, this is when an object is moving in a straight line. When an object starts moving in a circle, or when an object is spinning on its axis, Newton's second law of motion changes. Instead of F, which is a force, we end up with torque. Are we clear? So instead of F, we end up with torque, like this. Instead of mass, which is the inertia of an object moving in a straight line, we end up with moment of inertia, I, capital I. Instead of linear acceleration A, we end up with angular acceleration. So Newton's second law of motion, F is equals to ma. This is when an object is moving in a straight line. However, when an object is undergoing rotational acceleration, and this particular object, when we're talking about rotational acceleration, we mean that when an object is spinning faster and faster and faster. So there is rotational acceleration alpha. That rotational acceleration alpha is going to be caused by a torque. And since the object is undergoing rotational acceleration, its mass is what's going to become the moment of inertia I. So you end up with Newton's second law of motion written in terms of circular motion as tau. This is called tau, the torque. This is a Greek letter tau. Torque is equals to moment of inertia multiplied by angular acceleration. Is it clear? Where tau or torque is the torque acting on a spinning or a rotating object, then I is the moment of inertia of this spinning or rotating objects, then alpha is the angular acceleration of this particular object. So there is Newton's second law of motion also when objects are spinning faster and faster or they're slowing down as they spin on the axis. Is that clear?
Yes, sir.
Okay, so with that out of the way, example number 3. A certain 8 kg wheel has a radius of gyration 25 centimeters. What is its moment of inertia? That's the first question. Question number 2. How large a torque is required to give it an acceleration of 3 radians per second? So this acceleration of 3 radians per second, this is angular acceleration. Now, for us to work out what the torque is, as we have seen from Newton's second law of motion in rotational motion, for you to work out what the torque is, you need to know what the moment of inertia is. You also need to know what the acceleration is, the angular acceleration. We have been given the angular acceleration, but for us to work out the torque, we first need to work out the moment of inertia. We know the mass of the object. The mass of the object is 8 kgs. We know the radius of gyration. The radius of gyration is 25 centimeters. So using this information, we can work out what the moment of inertia is. The moment of inertia I is equals to the mass of the object multiplied by the radius of gyration, which is k. Now our k is 25 centimeters. So and that 25 centimeters has to be expressed in meters. So we end up having moment of inertia is equals to 8 kgs multiplied by 0.25 squared. With that bit, you end up having your moment of inertia being equals to 0.5 kgs meter squared. So this is your moment of inertia. So in that case, now that you have a moment of inertia, it's now possible for us to work out how much torque is needed for you to cause the required acceleration. So the torque is going to be equals to the moment of inertia multiplied by the angular acceleration. Our moment of inertia we have found is I is equals to 0.5 kg meter squared, and the required angular acceleration which is supposed to be given is 3 radians per second squared. So you can work out your torque. So your torque is going to be equals to 0.5 kgs meters squared multiplied by this bit here. 0.3 radian second squared. So you end up with this kg. Then you get one of the m's here. So kg with one of the m's here multiplied then this bit here, you get meter second squared. So that meter second squared times this kg. So you end up with the Newton. Then the other bit, the other remaining m, this is what you use. This radian bit just disappears. So you end up with torque which is equals to 1.5 Newton meter. That's the required torque. So you are applying Newton's second law of motion to an object which is undergoing rotational acceleration of 3 radians per second squared. Are we clear?
Very clear on my part.
Yes, sir.
Okay. Next example, question number 4. Determine the constant torque that must be applied to a 50 kg flywheel with radius of gyration 40 centimeters to give it an angular velocity of 300 revolutions per minute in 10 seconds from rests. So a flywheel, those of you who have been to the gym, you have those bicycles where you are in the gym, but there's that bicycle thing you jump on, then you cycle it, but it's got a wheel which is heavy, which is made of some metal stuff. That's what a flywheel is. So a flywheel is just basically some cylindrical disc. So we know the mass of this flywheel. The mass is 50 kgs. We know the radius of gyration, that is 40 centimeters. So if we are going to look for torque, we know that torque from Newton's second law of motion, torque is equals to the moment of inertia multiplied by the angular acceleration, alpha. So in that case, we need to find the moment of inertia. First of all, we need to find the moment of inertia I. We also need to find alpha if we're going to get our torque. That's what we need to do. So we can work out what the moment of inertia is going to be since we know the mass and the radius of gyration. So moment of inertia I is going to be equal to the mass of the flywheel times the radius of gyration squared. Our mass is 50 kgs and our radius of gyration is 0.4 meters. So this thing 0.4 is supposed to be 0.4 meters squared. Let's say 50 times 0. Supposed to be 0.4 meters squared. So the squared is missing, but the result comes out to be this. So there's a squared which is missing here. So if you have printed out the notes, you put a squared there. So the squared is missing there. Okay. So this is our moment of inertia, like this. Now, so I found our moment of inertia. The other bit we need to find is this, the angular acceleration. We know that it starts from rests all the way up to 300 revolutions per minute in 10 seconds. So this information which you have here is representing angular acceleration. So in our case, alpha is going to be equal to omega f minus omega I divided by t. Our omega I is when this particular object starts from rest. Our omega f is the 300 revolutions per minute. But as before, these things have to be changed from revolutions per minute to radians per second if you're going to do anything. So in our case, our omega I is basically 0 revolutions per second, which is just 0 radians per second. Then our omega f is 300 revolutions per minute. So this 300 revolutions per minute has to be changed to radians per second. So you end up having omega f, which is equal to 300 revolutions per minute, which is 300 revolutions divided by minute, 300 revolutions per minute times 2 pi radians divided by a revolution multiplied by 1 minute divided by 60 seconds. So you end up having 31.4 radians per second. So that is your final angular velocity. So your final angular velocity is this much. Your initial angular velocity is that much, since this particular thing is starting from rest. So you can work out your angular acceleration. Alpha is going to be equal to omega f minus omega I divided by t. So your alpha is going to be 31.4 radians per second minus 0 radians per second divided by 10. So this bit, 31.4 minus 0 radians per second is 31.4. Then 31.4 divided by 10, you end up having alpha is equal to 3.14 radians per second. So this is your angular acceleration. So our angular acceleration is alpha, 3.14 radians per second. Our moment of inertia, we have found up here, our moment of inertia I is 8 kg meters squared. So we can work out the torque. So in our case, the torque tau is moment of inertia multiplied by alpha. So in this case, we end up having torque equals to 8 kg meter squared multiplied by 3.14 radians per second squared, and we end up having our torque, which is approximately 25 Newton meter. So that's going to be our torque. Are we clear?
Yes, sir.
Okay, so that is about what you have to say about moment of inertia, and for now also what we have to say about torque. And you have looked at this connection between moment of inertia and torque with angular acceleration in more detail in the form of Newton's second law of motion for circular motion. The other kind of thing we have to start looking at is energy. Okay, rotational energy. Now, when an object is moving, it's in motion, it has got kinetic energy. Okay, but there is also kinetic energy which objects have when they are spinning. So when you have got a ball, let's say you play soccer, you kick this ball, and this ball is moving in a straight line. It's not spinning. Sometimes you can kick a ball and the ball doesn't spin. So the only kind of energy the ball has is the energy which it has as a result of moving in a straight line. That kind of energy which an object has when it's moving in a straight line, that is what's referred to as kinetic energy or translational kinetic energy. But there are also other times when you kick a ball, then it starts spinning. It's moving and it's also spinning. So there are two kinds of energies, kinetic energies there. There is kinetic energy as a result of the ball moving from point A to point B. There is also kinetic energy as a result of spinning. Are we clear? That energy which an object which is spinning has is what's also referred to as rotational kinetic energy. Another example is the tires of a car. The tires of a car will move in a straight line, but as they are moving in a straight line, they are also spinning. So the tires of a car have got two kinds of energies. There is energy because the car is moving in a straight line. That's what is called translational kinetic energy. But there is also kinetic energy because the tires are spinning. The kinetic energy which is as a result of the tires spinning, that is what is referred to as rotational kinetic energy. So you have to be very careful to check if this object you're looking at, is it just moving in a straight line or is it moving and spinning? If it's spinning as it's moving, then it has got more energy than just the energy as a result of moving in a straight line with a particular velocity. So in that case, it ends up having two kinds of energies. There is translational kinetic energy and there is also rotational kinetic energy. Now, for an object which is moving in a straight line, the kinetic energy Ke is equals to half m v squared. This is how we work out the kinetic energy for an object moving in a straight line. Now, for an object which is spinning on its axis, we work out the rotational kinetic energy in a similar fashion. The only thing we do is we replace the mass. Since the object is spinning, we replace the mass with the moment of inertia. Then we replace this v with the angular velocity. So we end up with rotational kinetic energy KER equals to half. This half is the half you're seeing here. Then this moment of inertia is because we are replacing the mass with moment of inertia. Then with this v, we are replacing this v with omega. Is it clear?
Yes, sir.
So far in this class today, we have done, this is a second direct replacement formula we are forming. There was Newton's second law of motion, F is equals to ma, where we replace the F with torque, where we replace the mass with moment of inertia, and we replace the A with alpha. Then here we have got this. Kinetic energy is equal to half mv squared. Now, this is kinetic. This is the energy of an object moving in a straight line. If the object is spinning about an axis, it means that that particular object has got moment of inertia I, and it's spinning with a particular velocity omega. Then this particular object has got rotational kinetic energy, and the rotational kinetic energy is obtained by just making substitutions to this thing, where the m is replaced by the moment of inertia, and where the v is replaced by omega. We know how to get the moment of inertia, and maybe we'll be told how fast this particular object is moving. So the only thing we need to do, if we want to get out want to find out what is the rotational kinetic energy, is we need to get what the moment of inertia of the object is. We have seen how to get a moment of inertia, and we need to find out how fast this particular object is spinning. That's all. Then you get your rotational kinetic energy. So your total energy is going to be equals to the translational kinetic energy plus the rotational kinetic energy as a result of this particular object moving. So the total kinetic energy in this case, is going to be equals to kinetic energy translational plus rotational kinetic energy. That's going to give you total kinetic energy is going to be equals to half mv squared plus half moment of inertia multiplied by omega squared. This bit. This is how you get your total kinetic energy. You can have an object which is not moving. If the object is just spinning on its axis, it's not moving in a straight line. So if the object is not moving in a straight line, but it's just spinning on its axis, for example, when you have a car which is stuck in the mud, okay, when you've got a car which is stuck in the mud, this car is not going to move in a straight line, but its wheels will continue spinning. In that case, your V is going to be 0, but your omega is not going to be 0. Or if you have got it like the example I gave where someone hits the ball, then the ball doesn't spin, but it just moves in a straight line. If something doesn't spin, then omega is going to be equal to 0. Are we clear?
Yes, sir.
Okay, so let's look at example number 5. A wheel of mass 6 kg and radius of gyration 40 centimeters is rotating at 300 rpm. Find its rotational kinetic energy. So, if you want to work out rotational kinetic energy of an object, KER, that's going to be equal to half moment of inertia, then the angular velocity. So in this case, we know the mass of the object. Then we also know the radius of gyration, which is 40 centimeters. So with this mass and this bit here, we can work out what the moment of inertia is going to be. So the moment of inertia basically is just I is equals to the mass of the object and the radius of gyration, which you've been given is 40. You change this 40 centimeters into meters, so you end up with 6 kgs multiplied by 0.4 squared. So you end up having your moment of inertia I, which is equal to 0.96 kg meter squared. So the moment of inertia we have found. The other thing we need to find is what is the angular velocity. We have been given the angular velocity as 300 revolutions per minute, but we do not do calculations in the revolutions per minute. So you need to change your revolutions per minute, your 300 revolutions per minute, you need to change it into radians per second, and when you do that, you end up having this 31.4 radians per second as shown there. So with our moment of inertia I, which is equal to 0.96 kg meters per second, and our angular velocity 31.4 radians per second, we can work out your rotational kinetic energy, which is going to be equal to half moment of inertia omega squared. So that's going to be half 0.96 kg meters squared times 31.4 radians second squared. That whole thing, when you work it out, you end up having this. You end up having 474.3 joules or 0.47 kilojoules as your rotational kinetic energy. You notice that rotational kinetic energy has got the same units as normal kinetic energy, joules. Are we clear? Are we clear? Any questions?
Clear, sir.
Okay. Huh?
It's clear, sir.
Okay, next bit. Here. So what else? What other kind of physical quantities have got rotational counterparts? For example, some of these things you already know. Linear displacement, symbol is S. The angular or the rotational counterpart of linear displacement is angular displacement, symbol is theta there. For linear velocity, which is V, the rotational counterpart is angular velocity, that is omega. For linear acceleration, which is A, the rotational counterpart is angular acceleration, which is alpha. For mass, the symbol, which is M, mass is when you're moving in a straight line. When you're moving in a circle, we don't talk about mass, but we talk about moment of inertia, and the symbol is I. For force, force is when you're moving in a straight line, and the force is given by Newton's second law of motion, which is equal to F is equal to ma. When something is rotating, we don't talk about force, but we talk about torque. And torque is equal to tau is equal to moment of inertia multiplied by a. There's another physical quantity, linear momentum. Linear momentum is p, the symbol is p, that is equal to mass times velocity. However, if you've got linear, which is straight line, then you must have angular. So there's something called angular momentum. The symbol for angular momentum is not P, but capital L. Angular momentum, which is capital L, is equals to the mass is replaced by the moment of inertia. So here we replace the mass with the moment of inertia, and this velocity V is replaced by omega. So the angular momentum is equals to the moment of inertia multiplied by the angular velocity. We are just doing direct substitutions here. Are we clear? Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
There is also something called impulse. Since when we looked at impulse, we're looking at linear momentum. So more specifically, what we were looking at is something called linear impulse. Now, linear impulse is given by the force multiplied by the time. Now, if there's linear impulse, there's something called angular impulse. Angular impulse, in place of the force here, we put the torque. It's given by torque and time. Time is the only thing which doesn't change, which remains the same, which is treated the same whether something is moving in a straight line or it's moving in a circle. That's time. Are we clear? Time doesn't change. Time doesn't change to anything else. It's the same thing. Okay. Then there is translational kinetic energy, which is Ke equals to half mv squared. If there's translational kinetic energy, then there is also what's referred to as rotational kinetic energy, which is KER. That's going to be half moment of inertia omega squared. Then there is work. For you to do work, you push something moving in a straight line, so you make something move in a straight line. So the work was given by W, which is equal to Fs. Then there's cos theta at the end. But now in this case, we are assuming that we are making a simple assumption that the force and the displacement are in the same direction. So they're pointing in the same direction. So if they're pointing in the same direction, then the angle theta is 0. So we just end up with work is equal to Fs. Then there's something called rotational work. Rotational work, with rotational work, you replace the force with a torque, you replace the S with theta. So in that case, you end up with work, which is rotational work, being equal to torque multiplied by the displacement. Work is measured in joules. Then there's also power. Power, one of the expressions we came up with power was this one. Power P is equal to the force multiplied by the average velocity. So also, there is power rotational power being given by power P being equals to this force replaced by torque and this velocity replaced by omega. So you end up having power being equals to torque multiplied by omega. So that's very, very useful table. But you can still come up with these things by just substituting whatever you know in a straight line with the other stuff which is supposed to be in a circle. Okay. Any questions on this table?
No, sir.
All right. So let's push forward. Example number 6. Compute the rotational kinetic energy of a 25 kg wheel rotating at 60 revolutions per second if the radius of gyration of the wheel is 22 centimeters. So in this case, rotational kinetic energy KER is equal to half moment of inertia multiplied by omega squared. So we need to know what the moment of inertia is. We know we have the mass of the wheel. We have also been given the radius of gyration of the wheel, which is 22. Then we also know how fast the wheel is rotating in the revolutions per second, but we need to change those revolutions per second into radians per second. So for moment of inertia, it's a very straightforward process. I is equal to the mass multiplied by the radius of gyration. So in this case, you have got 25 kg times 0.22 meters squared. You end up with your 1.2 kgs meter squared. That. Then for our spinning, how fast this particular object is spinning. In this case, we have got omega, which is equal to 60 revolutions per second. That's equal to 60 revolutions per minute multiplied by 2 pi radians divided by 1 revolution. So you end up with 377 radians per second. That's your omega. So you can work out what your angular, your rotational kinetic energy is going to be. So your rotational kinetic energy, KER, is going to be equal to half I omega squared, and that's going to be half this your moment of inertia and your angular velocity squared. So you end up having KER, which is goes to this 85,988 joules, or basically approximately 86 kilojoules, as how much energy this thing has. We clear? We need to finish the energy part so that we only remain with the momentum part. Remember, we're talking about rotational work and energy, then there's momentum at the end. So I want us today to finish the rotational work and energy part, then we can remain with whatever comes after that. Question 7, example number 7. How much do you have to go? Okay. So have to finish at page 13. So let's target reaching page 13. Then we'll call it a day. The rest of the other stuff which is there, we can do it when we meet on Thursday. Okay. Okay, 7. A 6 kg bowling ball. So we're talking about a ball here. Starts from rest and rolls down a gradual slope until it reaches a point 80 centimeters below its starting point. How fast is it going? So we have got a ball which starts from rest and it rolls. Now when something is rolling, it's covering physical distance and it's also rotating. Now it's going down. Now one of the things which down the slope, one of the forms of energy which this particular object is losing is gravitational potential energy. And the gravitational potential energy which this particular object is losing is being gained as kinetic energy. So when the ball rolls off from rest to a height below 80 centimeters, it's losing gravitational potential energy. And we can work out how much gravitational potential energy it has lost, since gravitational potential energy is equals to the mass, then the g times the height. So the lost gravitational, the mass of this ball is 6 kgs, the g is 9.8, and the change in height is 80 centimeters, which is 0.8. So basically, the lost gravitational potential energy is 47 joules. That's how much gravitational potential energy it loses. However, this gravitational potential energy, when it's lost, it shows up as total kinetic energy. Are we clear? When this gravitational potential energy is lost, it shows up as total kinetic energy. The question we are being asked is, how fast is it moving? How fast is this particular object moving when it has this particular point 8 centimeters below? So we know how much gravitational potential energy has been lost. It's 47. The total kinetic energy, since this particular object is covering distance and also it's rolling, is going to be equal to KET, translational, plus KER. So we end up having total kinetic energy is half mv squared plus half I omega squared. Now, we know that for a ball, moment of inertia is 2 over 5 mr squared, as we have been given here. This, for a sphere, moment of inertia is 2 over 5 mr squared. So we have an expression of moment of inertia, which we are going to put here at I. But we also know that V is related to omega. So we know that V is equal to R omega. So we can make omega the subject of the formula. So we end up with omega is equal to V over R. So our total kinetic energy in this case, total kinetic energy is going to be equal to half mv squared plus half 2 over 5 mr squared. Then where there is omega here, we put V over R, then we square like that. When we do that, we're going to end up with total kinetic energy equals to half mv squared plus half mr squared, then v squared. This is v squared, then r squared at the bottom. This r squared and this r squared here will cancel out. So when this r squared and this r squared cancel out, you end up with half mv squared plus 1 over 5 mv squared. When you add these, half mv squared plus half of 5 mv squared, you end up with total kinetic energy being equal to 0.75 mv squared. Is that clear?
Yes, sir.
Yes, sir.
Yeah. The reason why we're splitting the kinetic energy like this is because this thing, apart from moving straight in a straight line, it's also rolling. So the total kinetic energy is a combination of translational kinetic energy and rotational kinetic energy. So this total kinetic energy is the energy which is gained. This gained kinetic energy is equal to the lost kinetic energy. So our 0.75 mv squared is equal to, now we do this. The reason why we're doing this is because we are assuming that there's conservation of kinetic energy. The lost gravitational potential energy is showing up as kinetic energy. So you end up with 0.7 mv squared is equals to 47. So our mass is known, that is 6 kg. So 0.7, 6 kg v squared equals that. So this, you multiply by that, you end up with this v squared. Then you divide both sides, so you end up with v squared is equals to 7, 4.2. So you do that, you end up with v squared is equals to 11.2 m squared per second squared. Then you take the square root on both sides of 11, you end up with velocity v equals to 3.3 meters per second. So it depends on what you're being asked to find. How fast is it moving? So we were forced to change the rotational part of the equation of the total kinetic energy into something which looks like, which has got units of straight line stuff. Are we clear?
Yes, sir.
Next, example number 8. As shown in figure number 3, a uniform solid sphere rolls on a horizontal surface at this much, 20 meters per second, and it rolls up the incline. if the friction forces are negligible, what will be the value of h when the ball stops? So basically, how much height is it going to gain? This is a sphere. So as it's doing this much at 20 meters per second, it's also rolling. Okay. So again, the total kinetic energy in this case, so the total kinetic energy is going to be equal to the translational kinetic energy plus the rotational kinetic energy. We know that translational kinetic energy is equal to half mv squared plus half I omega squared. Since it's a sphere, for a sphere, the moment of inertia I is 2 over 5 mr squared. Then we also know this expression v is equal to r omega, like this. So basically what we are doing is similar to what we are just doing, but we are just doing it in reverse. So in that case, we end up having kinetic energy total is equal to half mv squared plus this 1 over 2. Then there is this moment of inertia expression here. Then in place of this omega, we put v over r, which is what you have here. You square it. So when you do that, you end up having ke total equals to half mv squared plus this bit half 1 over 5 m r squared v squared over r, this r squared and this, they cancel out. Then we end up with this expression here, 0.7 mv squared as our total kinetic energy. So we know the mass of this particular object. The mass of this particular, the velocity is 20 meters per second. We also know, okay, the velocity is 20 meters per second. The mass is not known. And we're going to see that it's not necessary for us to know what the mass is. So this is our expression for total kinetic energy. So this total kinetic energy, since there is negligible losses due to friction, all this total kinetic energy is going to be translated into gravitational potential energy. So our ke total is going to be equal to the gravitational potential energy. And when that happens, so we end up having 0.7 mv squared is equal to mgh. So there is, as you can see, there is m this side, there is m this side. So we can cancel out the m. So when you cancel out the m's, we end up having 0.75 v squared is equal to gh, like this. So you can see that from the cancellation of the m's here, you can see that it was not necessary for us to know what the mass of the object was. Never was. Okay. So we're looking for the h. So we can make h the subject of the formula by dividing both sides by g. When you do that, you end up having h is equal to 0.75 v squared divided by g. We know how much v is. V is 20 meters per second, and we know how much g is. So we end up having h is equal to 0.7 multiplied by 20 meters per second divided by 9.8 meters per second squared. So we end up with a height of 28.6 meters. So that's how high our thing is going to go. Are we clear?
Yes, sir.
Always be aware, one, there is always conservation of energy. So if one form of energy is lost, it's going to show up as another form of energy. So in this case, our thing was losing, our ball was losing kinetic energy, and that kinetic energy showed up as gravitational potential energy at the end of it, at the end of this whole thing. However, the kinetic energy was not just kinetic energy, it was translational kinetic energy plus rotational kinetic energy. That's what it was. Okay. Okay, our last example, what I believe is our last example. 9. Yeah. Starting from rest, a hoop of 20 centimeters radius rolls down a hill to a point 5 meters below its starting point. How fast is it rotating at this point? So now we are being asked to find out how fast this thing is rotating. How much is the omega? So since it's going, as it's rotating, it's going to a height of 5 meters below. So this thing is going to lose gravitational potential energy. So the lost gravitational potential energy in this case, lost gravitation is equal to the mass of the hoop, then the acceleration due to gravity, and the height which has been lost. So basically, that's how much energy is going to lose. We don't know what the mass of the hoop is. And as I'm going to show, we don't need to know the mass. In the previous example, we have just seen that we didn't need to know what the mass of the ball is going to be. It's just any ball moving at that particular speed is going to go to the same height. So the amount of height which the ball is going to cover, like in the previous example, does not depend on how big this particular thing. Any particular ball moving at the same speed will definitely go to the same height. So the same thing applies here. It doesn't matter how heavy this hoop is, what the mass is. So the lost gravitational potential energy is going to show up as kinetic energy in this case. So, and that kinetic energy, since this hoop is going around, is going down to a depth of 5 meters, it's going to lose the gravitational potential energy. It's going to gain kinetic energy, but that kinetic energy it's gaining is a combination of translational kinetic energy, which is half mv squared, and also rotational kinetic energy, which is equal to half I omega squared. So the kinetic energy is a combination of translational and rotational. For a hoop, the moment of inertia I is just mr squared, and we know that v, which is the translational velocity, is equal to r omega. So what we're going to do, we're being asked to find how fast this particular thing is rotating. That's what we're being asked to find. So in our case, we are going to replace our moment of inertia with this mr squared. So here we're going to put mr squared. Then we're also going to replace our v with r omega. So here, where there is v here, v squared, we're going to put r omega there. So ke total is going to be equal to half m, where there's v, we replace with this bit, r omega squared plus half m r squared, then omega squared. So in this case, you end up having, when you do this thing this side, you end up having half m r squared omega squared. This side, you're also going to end up having with half m r squared omega squared. So you end up having half this side. When you add them, you end up having a total kinetic energy just being equals to m r squared omega squared. So this is our total kinetic energy, m r squared omega squared. Our lost gravitational potential energy is this bit here, mgh. So with conservation of energy, these things need to be equal. So when you apply your principle of conservation of energy, so you end up having your lost gravitational potential energy being equal to gained gravitational kinetic energy, and your total gained kinetic energy is this much. So you end up having mgh equals to mr squared omega squared. As you can see, I was trying to say that these things don't depend on mass. So there's m here, there's m this side. So you cancel out the m's on both sides. You end up only with r omega, with r squared omega squared equals to gh this side. We are looking for how fast this thing is going to be rotating. So what you're looking for is actually omega. So in this case, you divide both sides by r, you end up having omega squared is equal to gh divided by r squared. And you take the square root on both sides, so you end up with having omega is equal to the square root of gh divided by r squared. So with this now, you can find out how fast this thing is going to be spinning. So you have your g, which is acceleration due to gravity. You've got the height, which is change in height, which is 5 meters, and you've got the radius of the hoop, which is 0.2. So when you substitute these things here, you end up having 9.8 multiplied by 5 divided by 0.2 squared, then the square root of the whole thing. You end up having omega as 35 radians per second. So that is how fast this thing is going to be rotating. Are we clear?
Yes, sir.
Okay, so the 30 minutes I asked for, extra 30 minutes I asked for, is finished. So we have to stop here so that you can prepare for your next class. Unless there are any questions. If there are no questions, then we're going to meet on Thursday morning as usual, so that we can finish up this bit. We're only left with 10 pages. Okay, so we've come to the end. The recorded thing is going to be uploaded to YouTube right now, and the link is going to be posted in